Okay, from yesterday. Let's take our seats, let's turn around. Okay, laptops.
Close your laptop, John.
Close them up, please.
I believe.
What can you tell me about what we learned yesterday?
Forces.
There's 4 forces. How far are we on? I know the answer, I just want to know if you know the answer.
Unit.
That's one,
Centrifugal.
and gravity was the other. That's what we've discussed so far. Okay? So, what can you tell? Not the forces, but describe the ones that we have left. Don't name the force. Well, maybe you have to name it and know what it is they actually do. So name one. Gravity's out. We talked about that. Electromagnetic force, that is out. The weak force and the strong force. What's the difference between the naming? I understand that.
One's weak.
I said besides the naming, what would the difference be?
One has less.
Yeah, and maybe it's one we can't really remember, and maybe one where we're not really listening either.
Kinley knows.
Where we're not listening.
Emma! She's talking to you!
I was in a manner of speaking, yes. Okay. So which one has a subatomic particle that splits to form a proton and an electron?
Electromagnetic force.
Nope, not that one.
Strong force.
Not that one. The weak force does that. Strong force has to deal with the nucleus of protons. It keeps them from colliding, okay? But also keeps them huddled together because you might say there's a lot of times where chemistry and physics do overlap, and this is one of those times because when you look at this table, each and every red number there in this lower left-hand corner is telling that specific element has that many protons in it, okay? And that's how you actually identify an element, because one of the things you're going to learn when we talk about those next semester is, oddly enough, you could say that the abbreviations may be speculated to be the least important aspect that you see in each element's box. The most important aspect is the number of protons, because if they have a positive charge, which they do, and electrons have a negative charge, which they do, if they balance each other out, positive charges and negative charges, does that add up to 0? If you have 15 positive charges and 15 negative charges, what happens when you add those together?
0.
They add up to 0. And that gets to be more important when, for those of you who do go on to take general chemistry here, and then if you're really good, then you get to take what I'm erasing here, and that's some organic and then maybe some biochemistry as well. But these charges that we're talking about get to be more important when we start talking about compounds like this. You don't need to write this down. This is what we're discussing right now in the general chemistry class. Okay, so I think I got this set to about where we left off. It might not be exact, but that's what we are going to go with. And while we haven't started yet, next week, I know I don't have it written down yet. I would be led to believe that probably start reviewing on Monday and Tuesday, and then we'll have our next 2-part exam on Wednesday and Thursday, or Thursday and Friday. We will make that determination when that gets here. So it'll say it on the board, but we may choose to move it a day to the right. So that's what the plan is, as of right now. If that changes, we will make that appropriate change next week. But that's, in short, where we are going. All right. So how many of you are looking at this and saying, this is actually somewhat interesting? And I wouldn't expect, what do we have, 15? I wouldn't expect 15 hands to go up, because this is maybe a little further in depth than what you think you're capable of doing, and I would disagree. The reason that it is maybe confusing is because it's something that you have not learned yet. Just like these names of these ions that we have back here. It just looks like it's confusing because you haven't been taught that yet. Once you learn that, it's not that it gets to be repetitive, it's just something that you will then learn to understand. Just think of the first time you picked up your musical instrument or placed on your football pads, or what I would like to think, and I think maybe makes the most sense, is at some point for you volleyball players, do you start maybe in competitive volleyball playing when you're in 5th grade, maybe? I'm just guessing. So we turn back the clock 4 years. Does that seem like it's a long time ago already, or no? So you're serving in volleyball. Oh yeah, take a deep breath. So are we serving like this in 5th grade yet, in 6th grade, or is it toss it up and hit it? Okay, well even so, just think of that first time where you had to learn to pick that up or throw that up and hit it. It's one of them things to where you just have not spent enough time on that. And I would like to think that's how we can view this concept, or whatever it is we're talking about here. We just have not learned it yet. Okay, so we will continue with Dr. Green here on the show Nova, thanks to South Dakota Public Television, and away we go, maybe. At least that's the goal. I just got to get this put on the screen now. Okay. Let's cooperate here now.
Who's 0-6? What's the Cowboys? I don't know, but I'm pretty sure they say this is our
And
year,
voila.
I swear to
There we
God.
go.
And they lost
Okay.
by like 20 to the Lions. They're good.
This is about where we left off with.
He certainly had motivations. Probably one of them might have been aesthetics, or this quest to simplify. Another one might have been just the physical fact that it seems like the speed of gravity is equal to the speed of light. So if they both go at the same speed, then maybe that's an indication of some underlying symmetry.
But as Einstein began trying to unite gravity and electromagnetism, he would find that the difference in strength between these two forces would outweigh their similarities. Let me show you what I mean. We tend to think that gravity is a powerful force. After all, it's the force that right now is anchoring me to this ledge. But compared to electromagnetism, it's actually terribly feeble. In fact, there's a simple little test to show this. Imagine that I was to leap from this rather tall building. Actually, let's not just imagine it. Let's do it. You'll see what I mean. Now, of course, I really should have been flattened, but the important question...
Okay, we're not in elementary anymore. All right? Okay?
Question is, what kept me from crashing through the sidewalk and hurtling right down to the center of the earth? Well, strange as it sounds, the answer is electromagnetism. Everything we can see, from you and me to the sidewalk, is made of tiny bits of matter called atoms. And the outer shell of every atom contains a negative electrical charge. So when my atoms collide with the atoms in the cement, these electrical charges repel each other with such strength that just a little piece of sidewalk can resist the entire Earth's gravity and stop me from falling. In fact, the electromagnetic force is billions and billions of times stronger than gravity.
That seems a little strange because gravity keeps our feet to the ground, it keeps the Earth going around the sun. But in actual fact, it manages to do that only because it acts on huge, enormous conglomerates of matter. You know, you, me, the Earth, the sun. But really at the level of individual atoms, gravity is a really incredibly feeble, tiny force.
It would be an uphill battle for Einstein to unify these two forces of wildly different strengths. And to make matters worse, barely had he begun before sweeping changes in the world of physics would leave him behind.
Einstein had achieved so much in the years up to about 1920 that he naturally expected that he could go on by playing the same theoretical games and go on achieving great things. And he couldn't. Nature revealed itself in other ways in the 1920s and 1930s, and the particular tricks and tools that Einstein had at his disposal that had been so fabulously successful just weren't applicable anymore.
You see, in the 1920s, a group of young scientists stole the spotlight from Einstein when they came up with an outlandish new way of thinking about physics. Their vision of the universe was so strange, it makes science fiction look tame, and it turned Einstein's quest for unification on its head.
Unification. Unification.
Led by Danish physicist Niels Bohr, these scientists were uncovering an entirely new realm of the universe. Atoms, long thought to be the smallest constituents of nature, were found to consist of even smaller particles, the now familiar nucleus of protons and neutrons, orbited by electrons. And the theories of Einstein and Maxwell were useless at explaining the bizarre way these tiny bits of matter interact with each other inside the atom.
There was a tremendous mystery about how to account for all this, how to account for what was happening to the nucleus as the atom began to be pried apart in different ways. And the old theories were totally inadequate to the task of explaining them. Gravity was irrelevant, it was far too weak, and electricity and magnetism was not sufficient.
Without a theory to explain this strange new world, these scientists were lost in an unfamiliar atomic territory, looking for any recognizable landmarks.
Then, in the late 1920s, all that changed. During those years, physicists developed a new theory called quantum mechanics, and it was able to describe the microscopic realm with great success. But here's the thing. Quantum mechanics was so radical a theory that it completely shattered all previous ways of looking at the universe.
Einstein's theories demand that the universe is orderly and predictable. But Niels Bohr disagreed. He and his colleagues proclaimed that at the scale of atoms and particles, the world is a game of chance. At the atomic or quantum level, uncertainty rules. The best you can do, according to quantum mechanics, is predict the chance or probability of one outcome or another. And this strange idea opened the door to an unsettling new picture of reality. It was so unsettling that if the bizarre features of quantum mechanics were noticeable in our everyday world, like they are here in the Quantum Cafe, you might think you'd lost your mind.
The laws in the quantum world are very different from the laws that we are used to. Our daily experiences are totally different from anything that you would see in the quantum world. The quantum world is crazy. That's probably the best way to put it. It's a crazy world.
For nearly 80 years, quantum mechanics has successfully claimed that the strange and bizarre are typical of how our universe actually behaves on extremely small scales.
At the scale of everyday life, we don't directly experience the weirdness of quantum mechanics.
But here, in the Quantum Cafe, big, everyday things sometimes behave as if they were microscopically tiny. And no matter how many times I come here, I never seem to get used to it. I'll have an orange juice, please.
I'll try.
I'll try, she says.
You see, they're not used to people placing definite orders here in the Quantum Cafe because here, everything is ruled by chance.
While I'd like an orange juice, there's only a particular probability that I'll actually get one. And there's no reason to be disappointed with one particular outcome or another, because quantum mechanics suggests that each of the possibilities, like getting a yellow juice or a red juice, may actually happen. They just happen to happen in universes that are parallel to ours, universes that seem as real to their inhabitants as our universe seems to us.
If there are 1,000 possibilities and quantum mechanics cannot with certainty say which of the 1,000 it will be, then all 1,000 will happen. Yeah, you can laugh at it and say, well, that has to be wrong. But there are so many other things in physics which at the time that people came up with had to be wrong, but it wasn't. You have to be a little careful, I think, before you say this is clearly wrong.
And even in our own universe, quantum mechanics says there's a chance that things we'd ordinarily think of as impossible can actually happen. For example, there's a chance that particles can pass right through walls or barriers that seem impenetrable to you or me.
There's even a chance that I could pass through something solid, like a wall. Now, quantum calculations do show that the probability for this to happen in the everyday world is so small that I'd need to continue walking into the wall for nearly an eternity before having a reasonable chance of succeeding. But here, these kind of things happen all the time.
You have to learn to abandon those assumptions that you have about the world in order to understand quantum mechanics. In my gut, in my belly, do I feel like I have a deep intuitive understanding of quantum mechanics? No.
And neither did Einstein. He never lost faith that the universe behaves in a certain and predictable way. The idea that all we can do is calculate the odds that things will turn out one way or another was something Einstein deeply resisted.
Quantum mechanics says that you can't know for certain the outcome of any experiment. You can only assign a certain probability to the outcome of any experiment. And this Einstein disliked intensely. He used to say, God does not throw dice.
Yet experiment after experiment showed Einstein was wrong, and that quantum mechanics really does describe how the world works at the subatomic level.
So quantum mechanics is not a luxury, something that you can do without. I mean, why is water the way it is? Why does light go straight through water? Why is it transparent? Why are other things not transparent? How do molecules form? Why are they reacting the way they react? The moment that you want to understand anything at an atomic level, as non-intuitive as it is, at that moment you can only make progress with quantum mechanics.
Quantum mechanics is fantastically accurate. There has never been a prediction of quantum mechanics that has contradicted an observation. Never.
By the 1930s, Einstein's quest for unification was floundering, while quantum mechanics was unlocking the secrets of the atom. Scientists found that gravity and electromagnetism are not the only forces ruling the universe. Probing the structure of the atom, they discovered two more forces. One, dubbed the strong nuclear force, acts like a superglue, holding the nucleus of every atom together, binding protons to neutrons. And the other, called the weak nuclear force, allows neutrons to turn into protons, giving off radiation in the process. At the quantum level, the force we're most familiar with, gravity, was completely overshadowed by electromagnetism and these two new forces.
Now, the strong and weak forces may seem obscure, but in one sense at least, we're all very much aware of their power. At 5:29 on the morning of July 16, 1945, that power was revealed by an act that would change the course of history.
What do you think it is? So 1945.
World War.
Nope, we're past World War I.
World War II.
So what would you guess really accelerated the end of World War II?
The nuke.
Yes, the hydrogen bomb. That's right.
In the middle of the desert in New Mexico, at the top of a steel tower, about 100 feet above the top of this monument, the first atomic bomb was detonated.
It was only about 5 feet across, but that bomb packed a punch equivalent to about 20,000 tons of TNT. With that powerful explosion, scientists unleashed the strong nuclear force, the force that keeps neutrons and protons tightly glued together inside the nucleus of an atom. By breaking the bonds of that glue and splitting the atom apart, vast, truly unbelievable amounts of destructive energy were released.
We can still detect remnants of that explosion through the other nuclear force, the weak nuclear force, because it's responsible for radioactivity. And today, more than 50 years later, the radiation levels around here are still about 10 times higher than normal. So, although in comparison to electromagnetism and gravity, the nuclear forces act over very small scales, their impact on everyday life is every bit as profound.
But what about gravity? Einstein's general relativity. Where does that fit in at the quantum level?
Quantum mechanics tells us how all of nature's forces work in the microscopic realm, except for the force of gravity. Absolutely no one could figure out how gravity operates when you get down to the size of atoms and subatomic particles. That is, no one could figure out how to put general relativity and quantum mechanics together into one package.
For decades, every attempt to describe the force of gravity in the same language as the other forces, the language of quantum mechanics, has met with disaster.
You try to put those two pieces of mathematics together, they do not coexist peacefully.
You get answers that the probabilities of the event you're looking at are infinite. Nonsense. It's not profound, it's just nonsense.
It's very ironic because it was the first force to actually be understood in some decent quantitative way, but it still remains split off and very different from the other ones. The laws of nature are supposed to apply everywhere. So if Einstein's laws are supposed to apply everywhere, and the laws of quantum mechanics are supposed to apply everywhere, well, you can't have two separate everywheres.
In 1933, after fleeing Nazi Germany, Einstein settled in Princeton, New Jersey. Working in solitude, he stubbornly continued the quest he had begun more than a decade earlier to unite gravity and electromagnetism. Every few years, headlines appeared proclaiming Einstein was on the verge of success, but most of his colleagues believed his quest was misguided and that his best days were already behind him.
Einstein in his later years got rather detached from the work of physics in general and stopped reading people's papers. I don't even think he knew there was such a thing as the weak nuclear force. He didn't pay attention to those things. He kept working on the same problem that he had started working on as a younger man.
When the community of theoretical physicists begin to probe the atom, Einstein very definitely gets left out of the picture. He, in some sense, chooses not to look at the physics coming from these experiments. That means that the laws of quantum mechanics play no role in his sort of further investigations. He's thought to be this doddering, sympathetic old figure who led an earlier revolution but somehow fell out of it.
It is as if a general who was a master of horse cavalry, who has achieved great things as the commander at the beginning of the First World War, would try to bring mounted cavalry into play against the barbed wire trenches and machine guns of the other side.
Albert Einstein died on April 18, 1955. And for many years, it seemed that Einstein's dream of unifying the forces in a single theory died with him.
So the quest for unification becomes a backwater of physics. By the time of Einstein's death in the 50s, almost no serious physicists are engaged in this quest for unification.
In the years since, physics split into two separate camps. One that uses general relativity to study big and heavy objects, things like stars, galaxies, and the universe as a whole. And another that uses quantum mechanics to study the tiniest of objects like atoms and particles. This has kind of been like having two families that just cannot get along and never talk to each other, living under the same roof. There just seemed to be no way to combine quantum mechanics and general relativity in a single theory that could describe the universe on all scales.
Now, in spite of this, we've made tremendous progress in understanding the universe. But there's a catch. There are strange realms of the cosmos that will never be fully understood until we find a unified theory. And nowhere is this more evident than in the depths of a black hole. A German astronomer named Karl Schwarzschild first proposed what we now call black holes in 1916. While stationed on the front lines in World War I, he solved the equations of Einstein's general relativity in a new and puzzling way. Between calculations of artillery trajectories, Schwarzschild figured out that an enormous amount of mass, like that of a very dense star, concentrated in a small area, would warp the fabric of space-time so severely that nothing, not even light, could escape its gravitational pull. For decades, physicists were skeptical that Schwarzschild's calculations were anything more than theory. But today, satellite telescopes probing deep into space are discovering regions with enormous gravitational pull that most scientists believe are black holes. Schwarzschild's theory now seems to be reality. So, here's the question. If you're trying to figure out what happens in the depths of a black hole, where an entire star is crushed to a tiny speck, do you use general relativity because the star is incredibly heavy, or quantum mechanics because it's incredibly tiny? Well, that's the problem. Since the center of a black hole is both tiny and heavy, you can't avoid using both theories at the same time. And when we try to put the two theories together in the realm of black holes,
They conflict, it breaks down. They give nonsensical predictions, and the universe is not nonsensical. It's got to make sense.
Quantum mechanics works really well for small things, and general relativity works really well for stars and galaxies. But the atoms, the small things, and the galaxies, they're part of the same universe. So there has to be some description that applies to everything. So we can't have one description for atoms and one for stars.
now, with string theory, we think we may have found a way to unite our theory of the large and our theory of the small and make sense of the universe at all scales and all places. Instead of a multitude of tiny particles, string theory proclaims that everything in the universe, all forces and all matter, is made of one single ingredient, tiny, vibrating strands of energy known as strings.
Okay, that's as good a place to stop as any. There's a few moments left that allow you to sit and reflect and recharge or whatever it is that after only a 4-day week, sometimes it seems like those are maybe a little more difficult to deal with than a 5-day week. Just imagining things, I don't know. But regardless, we'll see how next week shakes out, so we'll catch up to you next time.